Continuing our investigation into some very serious numbers about race and ethnicity and COVID-19 fatalities in New York City. Um, I want to remind you of some of the data that we're looking at here. This data comes from the COVID-19 tracker at health.ny.gov, and it records some disparities between the sizes of various racial ethnic populations and the incidence of COVID-19 fatalities among those populations. And so here, these are proportions predicted on the basis of the population size. This is basically the proportion of the population in each category here. And these are the actual proportion of fatalities in each of those categories. And you see, we would, if we expected that race had no bearing whatsoever, then we would expect all these observed proportions to be equal to the predicted proportions, but they're not. Some of them are lower, some of them are higher, and we don't really understand why at this point. It's probably a combination of a large number of factors. We're using these numbers to try to illustrate how to perform various hypothesis tests, and we've performed two hypothesis tests on these numbers. In the previous video, we tested the proportion of Hispanic fatalities against the predicted value and deduced that this difference between this 0.34 and this 0.29 is, statistically speaking, very, very significant. So again, I want to emphasize here that significant in the mathematical and statistical sense is not the same thing as important. Of course it is important. Of course it is significant in the common sense. We're talking about 3,301 people who died from COVID-19. So that's obviously significant. Here, I'm using the word significant also in the mathematical sense to mean that we can be certain that this is not due to chance. This is not due to a simple coincidence of these numbers, other things simply being equal. So we also performed a hypothesis test testing the mortality rates comparing the Black population to the white population. And we found that that was also very significant. In fact, the p-value, if we look back to it, was absurdly small, which means that it's very, very mathematically significant. And it's also socially and in the common sense of the word significant, very important and significant too. Now, I want to argue that these tests are arguably over-specific. So here we compared Blacks to whites. We didn't compare Blacks to Hispanics, whites to Hispanics, Asians to whites or Blacks or Hispanics. We only compared two categories with each other. Now, it would also make sense to ask ourselves a generalized question. Are there significant differences between all of these proportions and all of these? After all, we have 5 racial ethnic categories and 5 proportions predicted and 5 proportions observed. Can we say that the observed proportions are, in a statistically significant sense, different from the predicted proportions? Since we've already gotten 2 significant tests here, we would expect the answer to be yes. What the chi-squared test allows us to do is it allows us to synthesize all of these results. It allows us to prove that there is some significant difference somewhere. And since we've already identified where we found at least one significant difference, we will surely expect the chi-squared test to succeed. But nevertheless, we're going to carry this through as our first example of a chi-squared test. So the difference between a test of proportions and a chi-squared test is that the chi-squared test tries to assess whether there is any difference in multiple categories compared to some expected values in those same categories. So it's like a difference of proportions test for 3 or more categories. And so we can use all of our data at once and we can get a significance test. So here, the observed count is, these are actually estimated values as of 4/19. I used the proportion values and multiplied by the sample size. So these are estimated counts. And then the predicted counts would be on the basis of if everything were equal across the different, if everything were in proportion to the population. So, so the goal of the chi-squared test is we're going to test proportionality all at once. like any other tests, the chi-squared test has a null hypothesis and has an alternative hypothesis. The null hypothesis says that the fatality rates across all the races and ethnicities are going to be consistent with the overall population rates. Basically, these numbers are going to be those numbers. Now, even in the null hypothesis, though, we would expect some random variability. And it's much harder to describe the kind of variability because it's not just a variability in one number. Actually, all 5 of these numbers should, in a joint way, have some variability in them. And the null hypothesis predicts that and anticipates that. It says that these observed proportions should be targeted to be the values of these predicted proportions, but they should be subject to some standard error. And that standard error will affect all of them. They will all stray a little bit high or a little bit low from those predicted proportions. The alternative hypothesis says that the fatality proportions are different from the overall population rates. Notice that it doesn't say greater or lesser. It doesn't measure any particular one of them. It just says that they're different from. If 3 out of 5 of these are exactly in line and 2 of them are very much out of line, the chi-squared test will reject the null hypothesis on the basis of those 2, and it doesn't matter which 2. So this alternative hypothesis simply says that it's different from the overall population rates in any statistical way at all. So the chi-squared test is an all-at-once approach to establishing whether these proportions are different from some expectation for them. And so it's really, it's perfectly suited to this kind of question. It's also suited to any other kind of equity across categories question, whether they're racial categories or any other kind of categories. If we have different proportions in each category and we ask, does the makeup of, so for example, does the racial ethnic makeup of the US Congress reflect the racial ethnic makeup of the United States? And then we would probably, if we looked at the actual makeup, we would probably say, gosh, it looks like it doesn't. But the fact that it's slightly different might not be statistically significant. The chi-squared test would help you in that kind of case to assess whether that difference was probably due to chance or probably due, or definitely not due to chance, and help you establish that that was a statistically significant discrepancy between the racial ethnic makeup of our leadership and the racial ethnic makeup of our people. So that would be another case when we might want to do a chi-squared test. So how do we do it? Well, what I'm going to do here is I'm not going to do all of these counts and computations by hand here. What I'm going to do is I'm going to rely on the power of Colab, which is this interface that I'm working in. I have already imported, let me scroll up to it. I've already imported the package Scientific Python, which has the package stats. I've imported the package stats from that. And stats, that package, has a chi-squared test built in. And so all we have to do is we have to use this scipystats chi-squared package. And here's how we do it. We just have to get this vector of numbers, this vector of numbers, the observed counts, and this vector of numbers, the predicted counts, and we have to compare them by a chi-squared test. So I take the deaths and I pull out the column, which is the observed count. I could also write this this way, which might be more familiar. And then I get the deaths, and again, I pull out a column, the predicted count. So this is basically, this observed is basically this column of 5 numbers. This expected is this column of 5 numbers. The expected gives me the prediction. The observed gives me the actual measurement. And then I simply do this line. I simply ask the stats package to perform a chi-squared test on this, and it does. And so we're skipping over a lot of details here that we'll need to get to eventually. But I want to point out how powerful this is and what it gives us. This gives us something called a power divergence result. The important thing is it gives us the actual value of the test statistic here, which is the actual value of the statistic chi-squared, and it actually gives us the p-value too. We can ignore the test statistic because we're going to base the conclusion on the p-value. So it looks like the p-value is 4.8, right? How can the p-value be greater than 1? Well, it's not 4.8. It's 4.8 e minus 148, which means that it's this absurdly small number. It's 4.8 times 10 to the minus 148. This is the kind of astronomically small number, the kind of absurdly small number that most anybody but a mathematician would write with a zero. But technically, it's slightly larger than zero. But we have this minuscule microscopic p-value. And what does that mean? That means we reject the null hypothesis. That probably means we never should have considered the null hypothesis in the first place, maybe. But this is certainly our strong evidence that we should reject the null hypothesis. Now, here in the chi-squared situation, rejection of the null hypothesis is very strong, but is also somewhat ambiguous. It doesn't actually say what's going on here. What we've demonstrated is that the fatality rates across the races and ethnicities are not consistent with the overall population rates. In other words, what we've demonstrated is that we have a statistically significant difference between the overall breakdown of the population and the breakdown of those who are dying of COVID-19. Now, it says that there is a statistically significant difference between those things. It does not tell us what the directionality of the difference is. It does not tell us which groups are more likely to die or less likely to die. It doesn't give us any specifics, although of course we can get those specifics by looking at the data again. It tells us that the differences are significant, but it doesn't tell us which parts are most statistically significant. For example, like this is a huge difference, right? It doesn't identify specifically for us this huge difference as, oh, that's where you want to look for significance. And this is a huge difference, and that's very significant too. The chi-square test does not highlight and identify those things for us. It says somewhere in here, there is a significant difference. And really, it's a compilation of all the small differences here that gives us this strong result. So again, the question that we should leave ourselves with is why and what should we do about it? The fact that there is a statistically significant difference tells us that the effect is real. It doesn't tell us that the effect is large, though it is large. It doesn't tell us that the effect is important, though it is important. It simply tells us that this effect is real. It also doesn't tell us what's causing this effect. It doesn't tell us what we ought to do about this effect. So there are limitations to just working from the raw numbers here. The limitation is you can only see what the numbers will show you. The numbers don't show you the rest of life. They don't show you the conditions of New York City. They just show you the numbers. And so the numbers don't tell us the whys. They don't tell us what to do. They inform our ethical decision making, but they aren't enough. Our ethical decision making needs to figure out, needs to incorporate lots and lots of other information other than simple significance tests. But this is how we perform the significance test to demonstrate that the apparent trends here are real trends, and the apparent inequities here are real inequities. These are not due to random chance of sampling. These are statistically significant.